Hello, welcome back. Time to talk about salts as acids and bases. So classify each anion as a weak base or pH neutral. So remember the strong acids. The strong acids are HCl, HBr, HI, HClO4, and H2SO4. So one thing though, this is the first hydrogen only, first H only. So, and these are the strong acids, so they will not have a conjugate base. They will not react with water. So Cl minus, Br minus, I minus, oh, and I forgot nitric. HNO3, NO3 minus, ClO4 minus. These will not react with water. All others will. So, and they tend to react by ripping a hydrogen off. So, these ones will not. Therefore, nitrate, this is the only one that's neutral. So, and a base is a proton acceptor, and so NO2 minus is the conjugate base of HNO2, and acetate is, well, I guess it's not the H there. So this would be C2H3OOH. So the acetate, well, acetic acid here, and it does rip a hydrogen off. So this one here, so acetic acid is the conjugate acid to this. So these, both B and C, these ones are basic. So in general though, the only anions that are not going to react with water are the ones I've boxed in there, and those are the conjugate bases of the strong acids. HSO4 minus, this is a weak acid. So if you throw that in water, it'll form an acidic solution. So keep that in mind there. And okay, and I've just written there again. So pH, I guess that was more for my own notes. So the pH of a 0.1 molar sodium sodium formate solution. So how do you do this example? So you should know though that sodium, that means sodium's not going to react. It's going to be the formate anion. The formate anion is going to react with water. It's a weak acid, so it's not, remember, it's not one of these. So formate is not one of these. Therefore, it's going to react with water. So this is why I keep on telling you to memorize the strong acids. And you also have to understand the relationship, what it means to be a strong acid. So it will react, the formate anion will react with water, and it will form formic acid and hydroxide. And the conjugate base of the strong acid, of whatever acid, I guess weak acid, strong acid, Kw over the Ka, or Ka times Kb is Kw, and the Kb of this, the formate anion, is 5.6 times 10 to the minus 11. So let's start here initially. So we have 0.1 molar here, 0, 0, shift right, minus x plus x plus x, 0.1 minus x, 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 and our Kb, I know Kb before we went up there, Kb also means HCHO2, so formic acid, hydroxide, all over HCO. I guess that's CH. I tend to put the H first. CHO2. Like that. And we know that's 5.6 times 10 to the minus 11 equals x squared over 0.1 minus x, which is approximately x squared over 0.1. So that means 5.6 times 10 to the minus 12 equals x squared, or x equals the square root of 5.6 times 10 to the minus 12. So it's going to be 2 point something times 10 to the minus 6. Let's put that in our calculator. 5.6 e minus 12 to the 0.5. How many sig figs? 2 sig figs. X equals 2.37 times 10 to the minus 6. Okay, then we need the pH. So the POH, the pH is going to be equal to the 14 minus the POH, which is 14 minus a minus log of 2.37 times 10 to the minus 6. And let's put that in our calculator. 14 plus log of the answer, and we get 8.37 equals 8.37, and that is the answer. So that is how you do an example like this one here. So let me re-explain it. So how do you, we've mentioned before, so we know that this is a basic salt. How do we know it's a basic salt? Because it's not one of those ions. And those ions are from the strong acids, with the exception of bisulfate or hydrogen sulfate, because that's a weak acid. So it's not one of those. Therefore, it must be alkaline. But now you're saying, all right, we got to do this for a calculation. You have to know the Ka of formic acid. You can look that up, or it'll be given to you. So, oops, sorry. Oh, geez. Sorry for the pause there. If I move my iPad, sometimes it does crazy things. It reorients itself. I'm working on my iPad through my computer. Okay, so but we know that it's alkaline, and we'll either be given the Ka, or to look up the Ka for formic acid, and the fact that Ka times Kb is Kw will tell us, we can figure out, if we know one, we know the other, assuming we know the Kw. Kw for water is 10 to the minus 14 at 25 degrees Celsius, and is probably, unless noted, it'll be at 25 degrees Celsius. So we get our Kb is 5.6 times 10 to the minus 11, and then we write out the hydrolysis equation. So the writing out the hydrolysis equation, that's the CHO2 minus plus H2O in equilibrium with HCHO2 plus OH minus. That's considered common sense. You need to know how to write out the hydrolysis relationship. Then initial change equilibrium, initially 0.1 molar formate anion, shift right, write out the equilibrium expression, plug in your values, and get the hydroxide ion concentration. From that, calculate the pH. So, okay, into moving on. And for what about, those are anions. What about complete salts? So, so strong acid plus strong base yields a neutral salt. A weak acid plus a strong base yields a basic strong salt. Strong acid plus weak base makes an acidic salt. So the way I always remembered it was, if you have a weak acid but a strong base, it's so strong that the salt becomes basic, and a strong acid and a weak base, it's so strong that the salt becomes acidic. The real reason is that the weak acids and bases, their conjugates react with water, whereas the strong acids and bases, they do not. So so what's considered a strong base? The strong base for this it's going to be the alkali and alkaline earths. So the alkali and alkaline earths, in this case, these are going to be strong bases. Everything else is a weak base as far as salts and elements. But just the alkalis and the alkaline earths, and we've already talked about the strong acids and how they work. So let's apply this for these overall salts. So strontium chloride. So strontium chloride, that would be the result of the strong base strontium hydroxide and the strong acid hydrochloric acid. So this would be neutral, because that's a strong acid plus strong base. So B, aluminum bromide, that would be the weak base aluminum hydroxide, and the strong acid HBr. And because of the strong acid weak base, this is going to be an acid. And then C here, methyl ammonia nitrate. So methyl ammonia is so CH3NH2. That's going to be a weak base. And then NO3, that's from HNO3, so weak base and strong acid. This is going to be acidic. So that's weak base plus strong acid. Sodium formate, we even did an example of that just before. It turns out that strong base, sodium hydroxide, weak acid, formic acid, this is going to be a base. That's going to be an alkaline salt. So you're seeing here that's this case, the weak acid and strong base. Then ammonium fluoride, that's from ammonia, weak base, and hydrofluoric acid, weak base. You have no idea. You can't just look at this and know it. It turns out that HF is a stronger acid than NH4, so this one happens to be an acid. But you have to look to the relative size of Ka and Kb. Ka for HF is bigger than Kb for NH3. So, but you'd have to look that up. Let's see if you can follow. So, potassium acetate. Is this acidic, basic, or neutral? So what is potassium? Potassium is from the strong base potassium hydroxide. It's an alkali. Acetate, this is not any of these ions, right? Acetate is not one of those. Therefore, it's not from a strong acid. So we have a strong base and a weak acid. This is a basic salt. Okay, so and we also, next thing we'll talk about is polyprotic acids. So polyproton, so many protons. So sulfuric, we've already talked about, and the Ka for the first hydrogen and sulfuric is strong. Second one is weak, but it's still a pretty decently sized acid. The 1.2 times 10 minus 2, that's a pretty strong weak acid. So next, oxalic acid. If you ever get kidney stones, I've never got kidney stones, but kidney stones tend to be calcium oxalate. And there's oxalic acid in sweet potatoes, some potatoes, and taro. Taro has this in it too. So that's why we have to cook taro, is because to break up this oxalic acid, because it's abrasive. It can cut you. It can like cut your esophagus and digestive tract as it goes through. So you can see here sulfurous, phosphoric. I'm not going to go through all of them. And there's citric acid. It's a triprotic. So phosphoric, citric, triprotic. Ascorbic, that's the anti-scurvy acid I talked about before, and carbonic acid in our blood. There's even quadriprotic, so H4-EDTA. So ethylene diamine tetraacetic acid has 4 hydrogens. So you can have more than just 3. But how do you do these? Typically, basically, unless you have a huge number of sig figs, you can treat polyprotic acids as monoprotic acids, because the later ones become negligible, with the exception of sulfuric. So here is sulfuric, and I will show you the procedure for solving sulfuric acid, and this is a pain. Okay, so sulfuric acid, you have to look at it like a combination of a strong acid and a weak acid. The first dissociation constant is strong, so it completely breaks apart. I put a one-way arrow this way. So H2SO4 breaks apart into hydrogen ion plus HSO4 minus. So let's go ahead and do this. So initially we have 0.01 molar, 0, change is minus 0.01 plus 0.0, oh geez, too many zeros, plus 0.01 plus 0.01. Equilibrium is 0. It all goes away. 0.01, 0.01. So that's a strong acid. It breaks apart. Now we have a weak acid. A weak acid, initially this is 0.01 as shown right here. So this goes up there. So then hydrogen ion, we have 0.01, and sulfate 0. We shift right, minus x plus x plus x. So this is 0.01 minus x, 0.01 plus x, and then x. So that means our Ka2 is equal to H plus SO4 minus 2 all over HSO4 minus, like this. This equals 0.012 equals x times 0.01 plus x all over 0.01 minus x. And guess what? We can't disregard x, unfortunately. So we have to solve out the quadratic formula. So let's go ahead and do some math. So let's keep on down here. 0.012 times the quantity 0.01 minus x equals x 0.01 plus x. So I'm gonna now I have to FOIL both of these. So 0.00012, is that right? So that's right, 2 zeros there. Minus 0.012x equals 0.01x plus x squared. So now we have to get into ax squared plus bx plus c equals 0. Okay, and now we have to get the other variables on the other side. So this is going to be x squared, and we add the 0.012 plus 0.022x minus 0.00012 equals 0. And then we have to put it into the quadratic equation. Minus 0.022 plus or minus the square root of b squared. 0.022 squared minus 4 times a is 1, c is minus 0.00012 all over 2a, which is that. So x would then be equal to minus 0.027 or 0.0045. So you can't have a negative value there, so we pick this one as the proper solution. And then, so the x is that, so the 0.01 plus x 0.01 plus 0.0045. This equals the hydrogen ion concentration equals 0.0145. Yeah, 0.145 molar, and we need the pH. Is it the pH of that? Okay. So then pH is equal to minus log of 0.0145, which equals, so minus log of 0.0145. And this is how many sig? 3 sig, 2 sig figs? We have 2 sig figs with a Ka, so this is 1.84. And this is our final answer. Okay, so let me recap this one. So pH of 0.1 molar sulfuric acid. So when you look at sulfuric acid, you're kind of looking at two acids, a strong acid and a weak acid. The first thing that happens is the sulfuric acid breaks apart. So the 0.01 molar sulfuric acid is going to break apart in a hydrogen ion and bisulfate. And so then we have the second equilibrium here. We have the bisulfate at 0.01 molar, but has a hydrogen ion with a common ion 0.01 molar and no sulfate. So we shift right, and then we get the equilibrium value 0.01 minus x extent of reaction, 0.01 plus extent of reaction for hydrogen ion, and extent of reaction x for sulfate. And then we put in the equilibrium expression. So 0.012, the Ka for the second dissociation constant is equal to x times the quantity 0.01 plus x over the quantity 0.01 minus x. So we have to set that for the quadratic equation, use the quadratic formula to solve for it. Or you can, if you have your calculator that can do this for you, then geez, go ahead. This is a pain in the butt. We get two answers, pick the one that makes sense, and then we plug that answer. So we got x equals negative 0.027 and 0.0045. So we plug the positive solution into the hydrogen ion concentration being 0.01 plus that x extent of reaction, and we get the hydrogen ion concentration to be 0.0145 molar, and take the pH of that, we get 1.84 for that. Whew. That was always tough. Okay, so changing topics. So maybe the philosophy of chemistry. Why do acids act like acids? What is it? It's the bond strength. So the weaker the bond is to the hydrogen, the stronger the acid. So if you look here, and in the bottom we have HClO, and the chlorine and hydrogen, they're very electronegative, especially the oxygen. I'm going to draw electron density away from that hydrogen. So we have another oxygen to it. We're drawing even more electron density away from that hydrogen, making it really weak. Then we put 3 oxygens, and it's even weaker. Now we have the fourth with the perchloric. It's just a strong acid now. That hydrogen is not held on very strongly at all. So then what is happening is the electron cloud. So if you think of the electron cloud here, what's going on is the electron cloud is going more towards the oxygen, the chlorine here. The electron cloud is these oxygens are soaking it up, and then you add more oxygens. These are the electron vacuum cleaners. The electron density just gets pulled away from the hydrogens. Finally, when you get to perchlorate, it just pulls so much of the electron density away from it. It's a very polar bond, and the electron cloud has just about mostly moved over, and then it makes that hydrogen bonded to the oxygen very weak, and that makes it easy to pop off, hence the strong acid. And also, you'll learn about this in organic chemistry. If you take it, you'll refer to something as an acidic hydrogen. So these hydrogens here on methanol, these are not acidic hydrogens. This hydrogen there in the OH group, this is an acidic hydrogen. So this is reactive. Like for instance, if you throw methanol into to sodium, say if it takes sodium metal and you throw it into methanol, the sodium metal can rip off that hydrogen off the oxygen. So you'll form what's called the methoxy ion. And the methoxy ion is a very, very strong base. So you can use that for some gnarly chemistry if you want. So if you want to know a stronger base than sodium hydroxide, it's methoxy ion. So which one of the protons is more acidic? This one here has one oxygen. This one here has two oxygens attached close by. And A is a stronger acid. And also this C double bond OOH group, this is known as the carboxylic acid group. So this is a carboxylic acid. A is known as formic acid. That's formic acid. And B is methanol. It's an alcohol. Alcohols do have acidic hydrogens, but they're not really, water is more acidic than an alcohol. So, but a carboxylic acid is more acidic than water. So you throw it in water, it's going to be an Arrhenius acid or an Bronsted-Lowry acid. And also, there are some things that act as Lewis acid. So, I mean, you get certain reactions that occur where it's Lewis acid. And a Lewis acid, so I mentioned this before, that Lewis acid base works for everything. That's the most general. It's a better definition than Bronsted-Lowry. And because the reason why an acid is a proton donor is because the electrons, so here water is the base, and water is going to donate electron density to the hydrochloric acid, and adding the electron density will pop off that hydrogen from the anti-bonding orbital, and then that hydrogen will then attach itself to the water. So that is the actual process that goes on. That's how it works. So I mean, you could look at it. That's the best way, at least as far as where the electrons are going. You can get aluminum trichloride reacting with ammonia to form this molecule, this ammonium trichloride attached to ammonia. This is in fact an acid-base reaction. Likewise, you have trichlorobromide, or not bromide, I'm sorry, boron. Boron trichloride reacting with this with diethyl ether here can attach itself to the oxygen. So this again is an acid-base reaction. So and these are carried out not in water. And from this you can see many reactions that involve the transfer of electrons are also acid-base reactions. So it's kind of ties it to oxidation reduction in a way, but not every oxidation reduction is an acid-base reaction, and not every acid-base is an oxidation reaction. So be careful with combining these concepts, though, because so just a caution with that. But I wanted to show you that there are some acid-base reactions that do not occur in water, and the ones that do occur in water can still be described using the Lewis theory level of theory, and this is going to become more important later if you take other chemistry classes. So we are done for this, but we will continue talking about acids bases next chapter when we talk about buffers, but we'll talk about other aqueous equilibria other than buffers in the next chapter.